Good evening, everyone. It gives me immense pleasure to welcome you to today's webinar on behalf of the Center for Scientific Research and Development, People's University, Bhopal. Welcome to another exciting edition of the BioConnect webinar series, a platform led by the students for the students, designed to ignite curiosity, foster meaningful dialogues, and connect academic knowledge with real world challenges. My name is Pratyaksha, and I'm proud to tell you that I'm a BSc Biotechnology student and I'm honored to serve as your MC for today's session. Today's webinar focuses on the important theme green materials and energy technologies for tomorrow. In the face of growing environmental challenges and increasing global energy demands, the development of sustainable and eco friendly materials has become more important than ever. Green materials and advanced energy technologies plays a vital role in promoting renewable energy, improving energy efficiency, and reducing environmental impact. Today's session will offer valuable insights into how innovations in this field can contribute to building a more sustainable and energy efficient future. Before we proceed further, I would like to extend my heartfelt appreciation to the leadership of People's University, our respected faculty members, and the dedicated student team at CSRD whose efforts have made this event possible. We are deeply honored to have several distinguished personalities joining us today. I warmly welcome Professor Dr. Harish Rao, our Honorable Vice Chancellor of People's University, Professor Dr. Subhash Jay Bhore, Head of the Center for Scientific Research and Development and mentor for this initiative, Ms. Divyani Dangi, the Chairperson of the Organizing Committee, and most importantly, Professor Dr. Vilas G. Paul, our guest speaker, Professor of Chemical Engineering at Purdue University, Indiana, USA. We sincerely thank all our distinguished guests for joining us today and enriching this session with their presence. To formally set the stage for today's webinar, I now have the honor of inviting our respected Professor Dr. Harish Rao, our Honorable Vice Chancellor, to share his thoughts and officially inaugurate today's session. Sir, over to you. Please proceed.
Thank you, Pratiksha. Distinguished speaker, Professor Dr. Vilas P. Paul, respected faculty members, dear colleagues, students, and participants from across the globe. A very warm greetings to all of you, wherever you are joining us from across the world. It gives me immense pleasure to welcome you to BioConnect webinar number 50, a wonderful initiative of the Center for Scientific Research and Development, People's University, Bhopal, India. I am particularly delighted to note that this is a student-led program, truly reflecting the spirit of for the students, by the students. Such initiatives are a testament to the academic vibrancy and leadership potential of our students. Today's topic, green materials and energy technologies for tomorrow, is not only timely but also critically important. As the world faces pressing environmental changes, the role of sustainable materials and clean energy technology has become central to ensuring a better and more resilient future. Platforms like this webinar help bridge knowledge, inspire innovation, and encourage young minds to think responsibly and creatively. We are indeed privileged to have with us an eminent speaker, Professor Dr. Vilas P. Paul from Purdue University, USA. Sir, your distinguished contributions to the field of chemical engineering and advanced materials are widely recognized, and we are grateful to you for taking the time to share your insights with our students and participants today. Congratulations to the 6 student teams from the Center of Scientific Research and Development, People's University, for meticulous planning and preparing for this webinar. I also commend Professor Dr. Subhash Bhore, Head of the Center for Scientific Research and Development, for sustaining the momentum in organizing meaningful academic activities that provide valuable opportunities for students to develop diverse skills and learn from experts. This platform is also contributing to foster a research-driven ecosystem within the university. To all the participants, I encourage you to actively engage in today's session, ask questions, and make the most of this opportunity to learn from an expert of international repute. With these words, I once again extend a warm welcome to everyone present here. I wish the webinar a grand success and an enriching, immersive learning experience for all. Now I will hand it over to our MC. Pratiksha, over to you. Thank you.
Thank you very much, sir, for your inspiring words. Now, I invite the chairperson of the organizing committee, Ms. Divyani Dangi, to deliver the welcoming remarks. Ms. Divyani, over to you.
Thank you, Ms. Pratiksha. Hello, everyone. Our esteemed guest speaker, Professor Dr. Vilas Pol, our Honorable Vice Chancellor of People's University, Professor Dr. Harish Rao, respected dignitaries, our esteemed faculty members, or our mentor, Professor Dr. Subhash Paure, and my dear fellow students. My name is Divyani Dangi, and I am proud to share that I am a student of MSc Biotechnology at the Department of Biotechnology and Microbiology, Center for Scientific Research and Development, People's University, Bhopal, India. On behalf of the organizing committee, it is my great pleasure to welcome you all to BioConnect Webinar Session 15, a special student-led event organized by a dedicated team of biotechnology students at the Center for Scientific Research and Development, People's University, Bhopal. Today's webinar title, Green Materials and Energy Technologies for Tomorrow, addresses a highly relevant and impactful topic that lies at the intersection of innovation, sustainability, and responsibility. We are deeply honored to have with us our distinguished speaker, Professor Dr. Vilas Pol, Professor of Chemical Engineering at Purdue University, Indiana, USA, whose expertise and contribution in the field are widely recognized. On behalf of the organizing committee, I would also like to express our sincere gratitude to our Honorable Vice Chancellor, Professor Dr. Harish Rao, for his constant encouragement and for graciously joining us today to share his opening remarks. A special note of thanks goes to our mentor, Professor Dr. Subhash Paure, for his invaluable guidance, encouragement, and continuously support in making this event possible. I would also like to acknowledge and congratulate my fellow students, organizers. Their teamwork, creativity, and dedications truly reflect the vibrant spirit of People's University. With great pleasure, I once again extend a warm welcome to all participants. I encourage everyone to actively engage throughout the session. As we look forward to an inspiring and insightful discussion, I would like to hand over the program to our MC, Ms. Pratiksha. Ms. Pratiksha, over to you. Thank you.
Thank you very much, Ms. Devyani, for your insightful welcoming remarks and for setting the tone for today's session. Dear participants and fellow students, we are now ready to begin the core session of today's webinar. At this point, I'm pleased to hand over the session to our moderator, Ms. Rishita, who will introduce our guest speaker and moderate the session. Ms. Rishita, over to you.
Thank you, Ms. Pratiksha. Hello, everyone. A very warm welcome to all participants joining us from across India and beyond. I'm Rishita Maurya, and I'm proud to tell you that I'm a BSc Biotechnology student and a member of this webinar organizing committee at People's University, Bhopal, India. It is my privilege to serve as your moderator for today's insightful session organized under the BioConnect webinar series. Today's session focuses on green materials and energy technologies for tomorrow. It is my privilege to introduce today's guest speaker, Professor Dr. Vilas Pol, a globally recognized expert in the chemical engineering domain. Professor Pol currently serves as the Professor of Chemical Engineering at Purdue University, Indiana, USA. He is highly accomplished researcher and an innovator in the field of energy, storage, and advanced materials. Over the course of his careers, he has authored and co-authored more than 300 research publications, achieving an impressive H index of 65, reflecting the strong impact of his work in the scientific community. Professor Paul is also an active innovator, holding 27 issued US patents, along with the 10 additional patent applications. His research contributions have led significant technological advancements, particularly in material science and energy-related technologies. He has delivered over 200 invited lectures, including keynote, plenary, and TEDx talks, sharing his expertise with global academic and industrial audiences. In recognition of his outstanding contribution to teaching, research, and innovation, Purdue University has honored him with several prestigious awards, including the Outstanding Engineering Teacher Award, Most Impactful Inventor Award, Seed for Success Award, Bravo Award, and the Purdue Faculty Scholar Award. Professor Paul has received more than 20 prestigious awards from leading professional organizations such as the American Institute of Chemical Engineers, American Chemical Society, Material Research Society, the Minerals, Metals and Materials Society, and Institute of Electrical and Electronics Engineers. Notably, he was a recipient of the R&D 100 Awards in 2015, recognizing the world's most innovative technologies, and he also achieved 2 Guinness Book World Records. In addition, Professor Paul is a Fellow of the Royal Society of Chemistry and a Fellow of the Royal Society of Arts. His contribution has also been recognized with honors such as the Hind Ratan Award and the Asian American Engineer of the Year Award. Furthermore, he serves as the Fulbright Specialist in the field of energy storage. Through his primary research, mentorship, and global collaboration, Professor Paul continues to make significant contribution to science, engineering, and sustainable energy technologies. With this very brief introduction, it is my honor to invite Professor Paul to deliver the talk on green materials and energy technologies for tomorrow. Professor Paul, over to you.
Thank you very much for the kind introduction. It is also very wonderful to see that your university name is People's University and the logo says Beyond Limit. In fact, we have to have very big heart in mind that is beyond limit. And once you have that, such as you all have it now, that you would like to do something sustainable for the nature or live sustainably, and that's a really key thing, being in India, thinking about that and implementing the same ideology in your day-to-day life. So what I would like to do today is to give you a few examples. I will not be giving you too many details. However, I just wanted to direct you how you can think sustainably in a greener way when you are living your day-to-day life, and then we will have plenty of time for discussion. So let's begin. This is my research team at Purdue University. Those research team typically works on various aspects of energy storage, that is batteries, and that includes postdoctoral researchers, graduate students, some undergrads. Sometimes we do have visitors from around the globe. The whole team works on various aspects of energy storage, and that includes lithium-ion batteries, sodium-ion batteries, and next-generation batteries. Particularly, you have lithium-ion batteries in your cell phone, laptop, electric vehicle, and we also need the batteries for space applications. I do have some example to showcase. So this is our day-to-day work funded by various agencies, and we focus on various aspects of energy storage. However, the sustainability is a big aspect in that, and that's why we work on the sodium-ion batteries. For example, sodium is everywhere. It is abundant in the nature. We do not have to rely on different countries to obtain it. So one of the tasks or one of the work happening in our group is to work on the sustainable energy storage. More than that, we also want to make batteries safer than they are now. As you know, that energy storage device holds the energy, and that energy never wanted to be in one place. It want to release to the other form of energy. So we have to make sure that batteries are safe as well. Another thing we do in our group is develop batteries that work at extreme low temperature. So this is our day-to-day work. However, today's focus is not exactly batteries, but how we can make the materials for battery application or any other application in a greener way, in a sustainable way, creating less carbon dioxide to the nature. So a little bit about my background. I was graduated. I have 2 masters from Pune University. Dr. Subhash Bhore was my colleague at some point in Pune. So I have master in science and master of philosophy from Pune University, same as Professor Bhore. And then I left India back in 2001, went to Israel to pursue my PhD with Professor Aharon Gedankin. With him, I pursued my PhD. Then I met there Professor Doron Orbach. He's one of the best electrochemists in the world. And I had opportunity to work with him and get exploration to electrochemistry. Thereafter, my PhD, I joined Professor Ari Zaban at Bar-Ilan University, which is close to Tel Aviv. He is a president of the university now. And with his blessings, I worked with solar cell, desensitized solar cell. And then I was appointed at Argonne National Lab in Chicago. That is the first national lab of United States in Chicago area, where I initially appointed as Argonne scholar, then became a scientist and continued my career. Then I moved to Purdue University, where I am professor now for last 12 years. With that introduction, I would like to start how the materials, energy, and carbon cycle is interconnected. For example, the carbon-free energy is very materials intensive. We want that, we do not want to release carbon dioxide to the atmosphere, but then you use catalyst and many sophisticated things that takes lots of energy. Even the material production is energy and carbon intensive. Energy, the way we have it now, is very carbon intensive. So they are all interconnected, and that triangle never goes away. And we have to see where is the sweet spot in that triangle in order to continue working and making our future greener and brighter than what it is now. So energy. Everything is evolving, including our life. Without energy, nothing happens. Correct? As you wake up, you want to eat something that is energy. However, there are 2 major sources of energy we have today. And the first one is fossil fuels, where naturally you have the fuel underground that we dig down, get it out, and try to utilize. But when you burn that, for example, you have a car, you put the fuel inside and you are utilizing it, you generate a lot of CO2, and we would like to reduce that. So the idea is currently we use around 70% to 75% fossil fuel, and we would like to convert that fossil fuel to, let's say, renewable energy sources. And that includes solar energy, wind energy, water, geothermal, biomass. All those kinds of energy sources are wonderful. For example, the solar energy is the best source one can get. It is free of charge. Sun is shining all the time, particularly in India. There is no scarcity of sun. 12 months you have sun there shining on earth. However, storing that energy becomes an issue It's not easy. It's not let's say, economic. Now, even converting solar energy to electricity is also cost intensive. Namely, you have to have a solar cell. The efficiency of solar cell, silicon solar cell, is typically 15 to 20% photon to electron. So we lose a lot of energy while converting itself. So we have to come up with a solid idea that would help us to do that. So little more, who is the key player in order to make everything related to energy that is making it sustainable, economical, affordable, easily available, and so forth and so on. So actually, if you really think critically, everything boils down to materials. And if you can make the key materials, that would make the life easier and make things more sustainable, easily having a better efficiency that can be solar to electricity conversion or wind to electricity conversion. Everything boils down to materials. So where we can go and make the better materials, or ask a question to ourselves, what can we do in order to discover the new materials? So actually, you don't have to go anywhere. You can go to your high school book, where you do have a periodic table, and that periodic table have all the elements. And whenever we have some need, we start thinking about it, how to fulfill that need. For example, when we had a COVID problem, we had to come up with a vaccine. That was the shortest time ever any medicine or vaccine came to the market. So based on the requirement, we start imagining and creating, and the innovation come on the way. And that's the way whole the nature works and all the scientists work around the globe. So really, we have to imagine what we need to do. So I would like to give you an example of periodic table. You might have learned it and might have forgotten so far. So 1869 was the first time the periodic table of element started assembling by Mendeleev, Dmitry Mendeleev. He was a Russian scientist. Just imagine, 155 years ago now, there was no internet. There was no way that you can communicate from one country to other country except the phone. Even the phone was not readily available that time. So that time he was the first one to think about some element, iron, copper, nickel, whatever he could find. And he started putting the elements together based on their physical and chemical properties. Now, why I am stressing it? We need to really understand those elements from the periodic table, and that is the key for discovery of anything in the world. So 1869 also was the year where Purdue University, where I'm working now as a professor, was established. And 2019 was also 158th birth anniversary of Mahatma Gandhi. So in order to really motivate the student to think about the periodic table, go back and learn if you have forgotten, I wanted to set a Guinness World Record that you mentioned. And that is for motivation. And in order to know or teach you guys that you should know the periodic table, professors should know that too. So there was an assembly at Purdue University on August 15, that is our Independence Day, where I really wanted to write down the periodic table without looking in the book and showcase that I know that. But this was not the way to set the periodic table. There was bathroom tiles, 2-inch by 2-inch, on which the periodic table was written. Each element was written in the same color, and I had to assemble in front of the judge and hundreds of audience in the shortest time possible, and that was happening. So eventually, I was the first one to set a Guinness World Record to assemble the periodic table in the shortest time. So again, you are young generation, you really need to know your periodic table well. That will help you to discover anything required. For example, the cell phone everybody has today, that cell phone has minimum 40 to 50 elements from the periodic table. Just imagine that cell phone took all your devices. It took out the radio, it took out the traditional phone, no more cameras, everything is in your cell phone. What made it possible? Only the elements that people understood how to take the photonic property, how to take the magnetic properties and put them together in the smallest device possible. And then that cell phone became possible. So somebody dreamed hundreds of years ago that I would like to make a phone that will take care of hundred of other things at a time and make it very nice small device that you can carry. So somebody has to dream and things happens. And that's what you guys are dreaming now, to make the earth sustainable, greener. And with that dream, you will be able to do that. Now, as we mentioned, that everything has to deal with the materials. Now, if you look at the global map and try to find out where we are, what India has, what United States has, and what other countries has. These are the elements you can see yourself. China has the maximum amount of element, all important element they have. That's why no wonder they can lead all the technologies. They are the one to produce all the technologies, and then eventually we are the one becoming buyer of that. India has only chromium and not many other elements available. Australia has certain elements, United States has, Brazil has, and many other countries. So the elements, naturally, they are not in your country. They are everywhere in the world. Now, whatever we have, what can we do with that? And what we do not have, how can we use sustainably? That's the focus of today's discussion. So now when we say sustainable material, there are certain things we have to be careful. The material has to be easily available with minimum cost possible. When you are generating that material, that should not generate too much carbon dioxide. Or if you are trying to make a new material that you believe it will be sustainable, it has to be scalable. Just making small development in the lab that is never scalable, never coming to the market is not enough. Now, whenever we are discovering material, we also want a material that is high performance material, because just developing new solar cell, but that solar cell is not efficiently converting photonic energy or the sun energy to electron is also not useful. So all those parameters are very important when you are developing anything that you would like to call sustainable. So I will give you one or two examples today that would help understand how can you make materials sustainably. For example, we are from developing country like India. I am really proud to be Indian or Indian born, and India is doing really great today. However, we can do better with our growing population, growing economy, and many things. And the topic that we chose today is sustainability, where we have lots of plastic in India. So figuring out such topic is not a big deal, correct? You have trouble everywhere, plastic is everywhere. So what can you do with the plastic? By the way, plastic is nothing but the two elements from the periodic table, carbon and hydrogen. Latest element from the periodic table, they come together, they unite, they make a polymer. And there are hundreds of applications of the polymers. That's why we want them. We cannot take polymers away from our life. So if we cannot take away from our life, then how can we use it without contaminating our earth? Because they are having their own advantages and own disadvantages. They can choke your drains, they can go to the river, they can hurt the animals in the ocean, and so forth and so on. So these are the typical example I brought for you today to learn what one can do, and that can be making the material out of waste plastic, and that can be very useful for various applications. For example, if you have a research lab or you buy a laptop or electronics, it comes with some packing peanuts. Those packing peanuts can be made from two ways. One can make it from polystyrene. The other way is starch based. In US, we have lots of starch. We have cornfields. So typically we make it from starch. That can be degradable, but there are additives and things like that. So we cannot just throw it away. So when I was establishing lab myself, I was trying to figure out what to do with all these boxes coming with packing peanuts. And it is really a big trouble for everyone that we take out our electronics and then trash that box with packing peanut inside. And if it is polystyrene based, then it is really difficult to recycle or upcycle. So what can we do with it? So there was a postdoc, his name is Vinod Kumar Itacheri, Indian-based person. I asked him that can we bring all those thrown away packing peanuts and we will convert into the carbonaceous material in a sustainable way. Nothing goes to the atmosphere and use that material for battery application. And we did that. Those packing peanuts we bought inside the lab, we pyrolyzed that in inert atmosphere. If it is just starch-based, starch is nothing but carbon, hydrogen, and oxygen. If you put the inert atmosphere and heat it up, you do not release carbon dioxide or carbon monoxide to the atmosphere. You convert that starch to carbonaceous material at around 600 degrees Celsius. So we don't want to have anything energy intensive as well. And eventually we could make the batteries. Those batteries can power up your cell phone, laptop. And we demonstrated that batteries are not only made, but they are working. And there is some evidence how we made that work. Now, these are the scanning electron micrographs that needs electron micrograph. Electron micrograph is much more powerful than your optical microscopy. Optical microscopy could resolve up to, let's say, 10,000 times or 20,000 times. But if you want to see something really, really small, you need the electron microscope, where we shine the light on the surface or electron beam on the surface and backscattering electron generate the image, and that's what the images you are seeing here. So left side panel here, top left is of starch. That is the packing peanut we throw inside the furnace. And top right, you can see that that is the carbon materials you got out of it. And not only very small scale, on the right side, you can see that we work with a company called as Sure Carbon. They are the producer of carbon for various applications. And we made kilograms of that carbon just from the packing peanuts without hurting the environment or atmosphere. Now, for example, plastic is very, very difficult to recycle. It takes hundreds of years to decompose. When it decomposes, it becomes microplastic. It goes to ocean. Eventually, fish can eat it, and that can come to our cycle. Human would eat the fish later. But this technology, where you are trying to convert into carbonaceous material, you dissociate carbon-hydrogen bond, release the hydrogen, get the carbon back, and use it for various other applications. That can be carbon dioxide capture, that can be printer toner ink that you are using. One can use that carbon for filtration technology. Even your tire industry, all of your car tires are black. And the reason for that is we use 20% carbon in the tire to dissipate the heat, making sure that your tire does not explode when it has a friction on the road. So there are multiple applications of that carbon. When you zoom in to the carbonaceous material, it looks like a very thin sheet of carbon. So it designed actually very wonderful material that can store the lithium ion or sodium ion very effectively. And when we put it under the transmission electron microscope, it looks like a spaghetti. It is like a carbon-carbon bond organized in a way that it is a disordered form of carbon prepared at lower temperature. Now we use more scientific attitude and abilities to understand whether it is carbon or some other material. So we started with a packing peanut that we took in the beginning. We put it in the thermogravimetric analysis. We heat it up and check exactly what temperature this material is fabricating. There is another microscopy discovered by C.V. Raman. He got a Nobel Prize in 1930. That is the Nobel Prize. I remember India has discovering the Raman spectra, where you can probe the structure of any material. We utilize that. These are the signal coming from packing peanut, and that disappeared, and there are only two signals coming that is belongs to the graphite, and that tells you that this is a carbonaceous material and nothing else, no other additives, no metals into the system. So making sure that this is a pure form of carbon. X-ray spectroscopy, everybody knows that we use the X-ray for human to check our bones are okay and things like that. We can also use the X-ray to check and probe the materials and check their purity. Here, the X-ray demonstrates that this is a carbonaceous material prepared at various temperature in order to optimize what is the best temperature to get this carbon from packing peanut. Once we have the material, we wanted to make the batteries. So we put the battery electrodes together in a casing, and this is the schematic diagram for that. And then the batteries are perfectly working well. So what we are learning here is you take a trashed material, nobody wanted it. We took that, we converted into, let's say, carbonaceous material. Carbonaceous material act as an anode material, negative electrode for your batteries. Your battery has positive electrode and negative electrode. One of the electrode material made from these carbonate plastic waste. And now these batteries are working very happily, delivering very high capacity, as can be seen from the top left diagram. Our top right diagram also says that even when you try to charge and discharge battery with 1 hour time, 1C rate means 1 hour of charging, 1 hour of discharging, you still get very reasonable specific capacity out of the battery. And these batteries can charge and discharge for hundreds of times. We also study the impedance spectroscopy. Just wanted to make sure that impedance spectroscopy measures the resistance into the system. When you have a battery made from this packing peanut, one can think that this trash should not work well, or trash derived material should not work well. In fact, this material works better than your traditional graphite that you can buy from the market with minimum resistance in the system. And this is originated from this thin sheet of carbon where the Now, once we inside the battery, we also wanted to make what happens to those sheets when we cycle or charge, discharge the battery for hundreds of times. The top panel shows that these are the sheets with some binder we put it inside. And after lots of cycle, charging and discharging, these materials sustain inside the battery, does not decompose, does not degrade. So this sheet-like morphology remains like a sheet. And then we did again the structural analysis that has additional signal here that is belongs to lithium carbonate. That is the byproduct of decomposition of electrolyte forms inside the battery during the charge and discharge. However, the carbon sheets remain the carbon sheets, and they were cycling or charging and discharging the battery. So long story short is we make the one material sustainably that acted as the anode material for batteries, and batteries were very good. So I will not switch back and forth, but you can remember this packing peanut power supply. That is the video online on YouTube that is out of our research group, highlighted by American Chemical Society. As you can see that in few days, it got to 266,000 views worldwide. People really like something sustainable discovery. And this video is one of the demonstration that how can you take the material and make it sustainably that can be useful to power up your cell phone. Now, since we are talking about the environment, we also checked when we make something in a larger scale, are we releasing some carbonaceous material to the atmosphere, just like shown here. This is a cover art of the journal published in Environmental Science and Technology. Actually, those particles we were not able to see, but we were releasing some of the particles in our initial stage. So we decided to take or trap those particles and put that argon atmosphere or nitrogen atmosphere back to the system, making whole system green and nothing released to the atmosphere no carbon dioxide, no carbonaceous material that can harm the society. So again, this system starts with the packing peanut waste. We can scale it up, can get kilograms of carbons. That carbon look like a sheet, like architecture. And there was a company in United Kingdom called as Faradion. They were the first one in the world to make sodium-ion batteries. You might have heard that alternative or in complementary to lithium-ion batteries, we are developing sodium-ion batteries, as sodium is available everywhere in the world. They were the first one. This company is bought by Reliance a few years ago for $100+ million. And now India is developing this sodium-ion technology. But we were the first one to work with them to utilize this sustainable carbon developed from our lab and their cathode material, and showcasing those batteries are working for hundreds of cycles without any problem. So this work was done at Faradion, UK, where Dr. Barker was our collaborator from the company. And you can see that batteries are charging and discharging. Those are the initial phase of sodium-ion batteries. And the anode material for those batteries were developed by us from packing peanuts. As you can see that there are batteries who cycle for 300 cycles with minimum capacity loss. And so if you design well, even the materials produce sustainability could work very well for the battery application. Now I would like to switch gears to something even better than that. Plastic bags that you are facing trouble today or all the time, that we generate it, we try to recycle it, but we recycle, make another plastic bag, and eventually it goes to the atmosphere. So my idea is not to recycle, but upcycle. Upcycle means take something valueless and make something highly valuable, enhancing the value of that material. So back in 2010-12, we were also making materials that is carbonaceous material, dissociating this plastic bag in a closed container, making sure that we again do not elaborate or expose anything to the environment. And eventually we could make carbonaceous material, very nice black particles, spherical in shape, and carbon nanotubes. Now you might think that why do we need spherical shape? Actually, carbon is not a spherical material. Carbon is a layered material, hexagonal material. So anything you make with carbon makes a layered type of architecture, but not spherical. This is the first technology ever reported that can make something spherical, dense, particle of carbon within a closed reactor. And how did we do that? We use very simple technology to do that, and I will showcase. So the problem of plastic waste, everybody has it, but how you look at it, just like APJ Abdul Kalam says that creativity is seeing the same thing. Everybody has a plastic waste problem, but how you think about it to upcycle from the trash material, that's the beauty of your mind. So what I did was develop a reactor where I wanted to take your plastic waste, put it inside the reactor and heat it up. But I wanted to heat it up in a closed reactor fashion. So I developed a reactor from the scratch. And then after heating up, I knew that carbon-hydrogen bonds will break down. I will take out the hydrogen gas, put it in the cylinder, and I really want that carbon. Now this reactor, especially developed for this reaction, has multiple advantages. Namely, it is a single-step reaction. You don't need any solvent. It is a dry reaction. You just need a solid plastic waste and it becomes carbon. It makes pure form of carbon. You don't need acid or base or water to clean it up later. And the temperature is not too high. The reaction is carried out at lower temperature because when the hydrogen is released, it creates a pressure. You can hold the pressure together, eventually making sure that everything is in a greener shape. And same time, once you cook something under pressure, it gets cooked at lower temperature. For example, from your house is a pressure cooker. When you cook your rice inside the pressure cooker, The water boils, you have a steam coming out that prepares a pressure inside the reactor or a pressure cooker, and eventually you cook your rice much faster at lower temperature under the pressure. And that's the way I wanted to cook this plastic inside this reactor, making sure that we get this quickly. So the left panel showcase that is the best carbon one can make for battery application. It is somewhat potato shape, and we need a spherical shape of carbon for battery application as you charge and discharge battery every day. If you have a spherical shape, there are advantages to make the batteries safer, and we would like to make that. So the right side picture, you can see that the spherical carbon particle we made from this plastic waste, they are completely spherical dense. The properties of the material is very similar. That is very expensive today to buy from the market, but you can make it sustainably from plastic waste. We did a lot of science behind it to understand how we are developing this material. So we took the small reactor, put it in front of the X-ray. We have an advanced photon source, which is a high energy X-ray. And it is showcasing in this plot how you are converting this plastic waste all the way to carbonaceous material. So we started with room temperature, we heated to 700 degrees Celsius. We waited there, nothing happened, and then we started cooling down. So this is the way we understood the mechanism of formation of material, and we understood that around 350 degrees Celsius during the cooling, we make this carbonaceous material. So all the students who are doing doctoral philosophy degree, they have to do something very scientifically strong, and that was the way they were developing this mechanism. Now we wanted to take it under the microscope and see exactly how we organize those carbon-carbon bonds during the pyrolysis of plastic bags. And as you can see that at the top left panel, you can see the spherical nature of that carbon sphere. And when we continue to heat it up, it was become somewhat rough surface, but at the same time, it is maintaining its spheroidal morphology. Very high resolution TEM, transmission electron microscope, where you can see the atom of carbon, how it is aligned in a hexagonal fashion within the material. So although it is black in color, there is a beauty inside. We make the batteries out of it, and you can see that there are hundreds of stable cycles of batteries were achieved. So since we work on the batteries, we would like to check whether newly developed material is working for the battery application or not. Actually, more than just making the material and utilizing it, we also realize this material can make the battery safer than they are today. For example, you make the battery and we start heating the battery at higher temperature. We would like to have the thermal runaway of the battery. As you heat from the room temperature to higher temperature, as you can see that our material only generates 380 joule per gram exothermic heat. That is a differential scaling calorimetry. On the contrary, much higher heat is generated with those potato-shaped particles that we can buy from the market. So there are advantages to make the batteries, the electrode material, which is spherical in shape. As you mentioned that there was a R&D 100 award won in 2015. They select 100 best technologies in the world in order to figure out they are doing something innovative. This was one of the technologies selected for that. There are multiple videos on YouTube if you want to learn not only to make a spherical particle of those carbonaceous material from plastic waste, but we also made carbon nanotubes. Carbon nanotubes making is very difficult. You need catalyst, you need certain environment. Here we can make it from this trash plastic bag, and that was featured on PBS Nova, making things greener and cleaner under that title. So there is a YouTube video you can watch later as well. Now, this reactor was designed to upcycle the plastic. We did not stop there. We make anything required from the periodic table for various applications, battery application, solar cell application, magnetic application. And this is one slide showcasing that the same reactor that was initially developed for plastic upcycling, that can make wonderful material at lower temperature, for example, sulfides, phosphides, Carbides are the material which are very, very strong. Typically, aeroplane parts are made from carbides because it goes through various conditions. Nitrides are also very strong material, borides. So there is a review article where we summarize that anything you dream, you can make with this new reactor very effectively. Now that was related to recycling and upcycling of plastic, giving you some example on sustainability. Now, actually, we can think much beyond. And one of the example I wanted to bring out from Chandrayaan, you might have seen the news 2 years ago. India was the first country who successfully sent this Chandrayaan on the surface of moon, particularly south side of the moon, which is extremely, extremely cold. Now, in that cold environment, what do you need? You need power source, energy source. Actually, you might have heard the Chandrayaan is in the sleep mode now because the batteries they put there, that batteries used to, or were supposed to take a solar cell energy, convert photon to electron, and that electricity generated by the solar cell, put it inside the battery and move your Chandrayaan from one place to other place and send you some pictures. However, because of the south side of the moon gets extremely cold, batteries got frozen and they are not anymore acting or working. And that's why this Chandrayaan is in the sleep mode now, and we are trying to figure out how to make it active, generate enough energy with the small solar cell. To do that, we are developing some technologies for past several years, and I want to highlight a few of them quickly. For example, Neil Armstrong of Purdue was the first one to step on the moon. You all heard Neil Armstrong from your elementary school book, maybe fourth grade. He is our graduate. He is from Purdue University. 1969, Apollo 11, when we sent on the moon, he was the first one to go on that Apollo 11 and step on the moon. He graduated from us in 1965. He's with us, or his building is there now. I am working in the similar building. I teach here. So our idea was, why don't we develop a battery that is needed for space application where the environment becomes extremely cold, and making sure that we do have that energy required in that atmosphere. We also don't have to go to the moon or Mars. For example, your drones, they will be the one bringing to you pretty soon your postal service or whatever you ordered from Amazon. Now, in that case, drones will fly with high altitude. They will also need the battery, and that battery has to be sustained at low temperature. So there are multiple applications of the batteries. There is SpaceX and Blue Origin, where they want to take humanity to Mars and Moon. In order to do that, if you really go to the Mars or Moon, what you will need? First thing first is energy. You will have a requirement of the energy. And our idea is, can you just imagine we are on the surface of Mars or Moon now and generate the electricity from solar and convert into the electricity, put it inside the battery and use it for various applications. So if you have some dream in your mind, and that dream should be pull you, or the vision should pull you. And this is said by big people like this who discover your iPhone. So what we did is we went back to our material science and periodic table, and we started discovering some materials where niobium tungsten oxide, one of the cathode material that can be charged and discharged very rapidly. As you can see, 60 C rate, that is 1 minute of battery charging and 1 minute of discharging, you still get some reasonable capacity. We work with that material, and we wanted to make the battery that can work at ultra low temperature, solving the problem that we have today. This is the first battery where I am showcasing you that this was studied at minus 100 degrees Celsius. You may or may not know, on the surface of Mars and Moon, the temperature can go as low as minus 130, minus 140 degrees Celsius. It is extremely, extremely cold. However, we are very close to have a technology ready that can work at that environment without putting any heating coil or cooling system on the top. Our battery will work as is without sheltering it. So this is the first report. You get 75 milliamp hour per gram capacity during the discharge, and similar capacity get during the charge. And that lead us to set a new Guinness World Record. There was no record on the battery chemistry before, but this is the first one to make the battery that work as extremely low temperature. That was set in December 2022. If you have a 2025 Guinness World Record book in your house or in your office, if you open up 146 page number, this records shows there that how we discover electrolyte and electrode material with the team members that powers up at extremely low temperature. Now you have the batteries. You might think that what can I do with the batteries? I cannot take my cable from my home to the surface of Mars if I go to the Mars. So how I charge my battery there? So our idea was to charge and discharge the battery with the solar panel. Now everybody knows solar panel work on the rooftop of your house. However, the same solar cell works completely differently at low temperature. Namely, if you take a silicon solar cell, when the temperature goes down, the band gap widens. When the band gap widens, you get the more efficient solar cell. That is a beautiful thing. However, if you get a more efficiency, instead of 20%, if you get a 30% efficient solar cell at low temperature, you have to have a capability, that is battery, to store that energy. So there is a voltage current issue that you have to manage and generate certain voltage and put it inside the battery parallelly at a time or the same time. And this was one of the things we are discovering for the last several years, how to do that with our new battery technology with different solar cells. What I am showcasing here is, this is the first time ever we have charged the battery using the solar power at minus 105 degrees Celsius. So when the voltage goes up, battery gets charged, the current goes down. And then you take this battery and physically discharge it, play your cell phone or ignite the light or whatever you want to do that. So we are the first one to really harvest the energy at the surface of Moon and Mars or at that temperature, and then physically discharge that battery. Now we do have a device. The device can study the battery up to minus 170 degrees Celsius. So we continue to discover more new materials, understand that, and couple them with a solar cell. So you have a device getting ready to harvest the energy at extremely low temperature. Just imagine how sustainable it is. Today we have to take things from Earth, go to the Moon or Mars, and then finish that energy and come down. Now we want to create the energy there itself and utilize, and your Chandrayaan in future should be very successful with the help of that. Now there is a sodium-ion battery technology that I was talking about. This is the last slide where I would like to elaborate that sodium-ion batteries that we took. This is a Purdue campus where we put a small windmill. Since we want to do the sustainable thing, we want to harvest the energy from the wind in cold condition. As you can see that there is a snow on the ground. Everything is covered by the snow. And we put the battery on the top of snow where we wanted to show that battery can work at lower temperature without any heating or cooling system on the top. And the energy is harvested from the windmill. See, as you can see that we can charge the battery at low temperature with the windmill. So all the sustainable technology, we are a big fan of that. It can be energy from the wind, it can be from tides, it can be from solar sun. Once we have it, how we can capture it effectively and put it in the battery, even at extreme conditions, and utilize it. Now this is again very last slide where I wanted to showcase. This is a brand new cover page, came today on the cover of one of the journal. So we are making lots of batteries. The example is we are 8.2 billion people on Earth now. Everybody has minimum 2, 3, 4 batteries. Your cell phone has battery, laptop has lithium-ion battery, and you are throwing it away, or you don't know how to even recycle. Nobody knows in the world. So we put it in the drawer and it stays there, and somebody trash at some point. So actually our idea is, can we take those battery materials, some of the material is important like cobalt and lithium, take it out, and the remaining 80% of the material, what can you do? Where can you throw? We have plastic problem, and now we are creating more problem with batteries. Where can we throw them? So we actually are developing cement, that cement road or footpath or whatever way you wanted to use it, that can bury some of this recycled battery material that can stay inside and make the cement even stronger. So that's our idea, to make something sustainable, not to release too much CO2 to the atmosphere, but bury it inside the ground and stay down or keep it down. Another approach to make things sustainable. So with that, I would like to really conclude here. All this young generation, I would like to give few messages that if you have a dream to do something wonderful, you will be able to dream it, make an impact on your surrounding, your life, your family life, and so forth and so on. In order to achieve that, you have to have a strategic planning. Anything that you dream, it doesn't happen overnight. You have to dream, you have to continuously learn the material you need to learn in order to advance your knowledge. And you also need to know what is your strength, what do you exactly like to do. If you really want to do something related to sustainability, there are millions of things to do around you. You identify them, and you just want to do one good things in your life in order to make the life successful. And while doing that, never give up. Continue pushing the borders, and eventually good things will happen to you. So with that, I would like to stop here, and I will be happy to take your questions. Thank you.
Thank you very much, Professor Paul, for that highly insightful and inspiring presentation. Your discussion on green materials and emerging energy technologies has given us a deeper understanding of how innovative material science can contribute to a more sustainable future. We will now move to the interactive question and answer segment, where I will ask a few questions on behalf of our student participants, followed by the questions from the audience if time permits. My first question is, Professor Paul, your research spans advanced carbon materials, energy storage, and sustainable technologies. What initially inspired you to pursue research in green materials and energy technologies?
This is very nice, exciting question, and really suitable for the talk. As you can think that we are all from developing countries. Whenever I wanted to do research, there are people who want to do something really complex research. And I was thinking that I can develop something very sophisticated, but if it is not scalable and nobody can utilize it, or if it is not economical, then it is not worthwhile to do it. So the research has to be on something that is bothering you almost daily basis, correct? For example, plastic waste is bothering you daily basis. Even we are not even thoughtful how we are treating the plastic. If you think carefully how you are storing your garbage at home, you take a plastic bag and put garbage inside the bag, and when you are done, fill the bag, you actually tie the bag and then throw it away. If you are thinking that what you are doing with that is very bad, because you put your degradable let's say waste from your house, from kitchen and many things. Now, if you throw that in the nature, it should get degraded, but you put it inside the plastic bag and you tie the plastic bag. Now, nature cannot attack on it. Sunlight cannot go inside. You tied it and then you throw it away, and then somebody else will take care of it. But the plastic, as you know, that it takes 300 to 400 years to decompose. And if it decomposes by sunlight, eventually it will go as a microplastic to the ocean by rain. and then it is still a trouble. So not to have a technology that is just upcycling plastic, you have to actually get rid of the plastic once you are done using it. For example, take example of toys. We make most of the toys for children from plastic. Children use it for a month, two, and then throw it away, and eventually they go to garbage, and their garbage goes to a landfill and ocean. So actually, we are not getting rid of plastic. We are keeping the plastic more and more. Another example you can dream is COVID. COVID-19 came, and then we generated so much plastic on Earth. Even we put some of the dead people inside the plastic and then buried them or whatever we did. So we created actually more plastic, and we do not know how to effectively get rid of the first plastic that we have on Earth, and we are generating more and more. So actually, we have to think all the time, what are we doing and how can we get rid of it without harming the society and nature. So that was the driving force to make things sustainable. So the example of cement or example of making the battery that can work on Mars and Moon, this is all origin of this sustainability and need. Whatever we need to discover that ourselves. Nobody will come and help us out. So we have to initiate that. And that's the origin of my thought process.
Thank you for deepening our understanding of sustainable and eco-friendly innovations. My next question is for students who are new to this area. Could you briefly explain what green materials are and why they are becoming increasingly important in modern energy technologies?
So we are all materialistic people. We want more and more material, correct? We were okay with bicycles. Professor Bhore and I was very happy with MAT or small motorcycle. Now we all need cars. So we are making more and more materials that eventually goes to the cars. Car need combustion, gasoline. So materials remains a key thing. And we have to have them sustainable, correct? For example, we make the car, but at the end of the life of the car, after 15, 20 years, what is going to happen? Is that material is going to go back to the nature? Most of the time, it doesn't go easily back to the nature. It doesn't biodegrade easily. So those materials go on landfilling and staying there. At the same time, we have to extract the material to build the new cars. We cannot use that old car corroded material to build the new car. So whenever we are thinking about the green technologies, what is the origin of that material and what is the end of life of that material, we have to study the whole spectrum. For example, somebody told us that lithium-ion batteries are green, and if you use them in the car, then we do not have the exhaust pipe. Carbon dioxide will not come to the atmosphere. But we never study the whole spectrum of lithium-ion battery life, from where the lithium-ion batteries are coming, or the origin of the lithium and cobalt. And once we have the batteries, we put it inside the car, but how you are going to charge the car? You need electricity. And from where the electricity is coming? Today, even today, in this advanced world, we are burning the carbon dioxide in, let's say, out of 195 countries, 170 countries are burning coal even today to get the electricity. So if that is the scenario, then how can you believe that this electric car is making something greener? Because my electricity is not green. It came from carbon dioxide burning. So every time we think that it could be green, but it is never green. There is nothing 100% in this world. We always lose something. But minimum, we have to have a thought process whether it is making it green or not. Otherwise, without thinking, we are shooting in the dark and wrong places. So for the new generation, I would ask them to really go back to learn the periodic table, learn the properties of the elements, and see whether we are picking up the elements that are green, that are sustainable, that are available. For example, India wants to develop an electric vehicle and batteries. But as you saw in one of the slides, India doesn't have the raw materials. how can you ever develop that technology economically, sustainably in our own countries? So we have to be careful what we are trying to do. If you import everything, you pay taxes and tariffs. I don't think it is going to work out for longer run. So we have to be thoughtful. So you being young generation, you have to really go to the origin of the problem and then try to identify the material. Those material can do it efficiently with minimum energy consumption, energy requirement, and eventually economic. So those are the key parameters to look at while discovering or innovating anything new.
Your explanation made the importance of green materials in modern energy technologies very clear. Thank you. My next question is, in your opinion, what are some of the most exciting recent breakthroughs in green materials or sustainable energy technologies that could significantly impact the future of energy systems?
Yeah, there are some green materials, for example, alternative to lithium-ion batteries. We are discovering sodium-ion batteries. You know, sodium chloride we eat every day. So we have the sodium in Indian Ocean. Mahatma Gandhi did satyagraha for that, to have the sodium free without taxes, correct? So we do have that sodium. So developing the technology that is based on sodium is wonderful. A lot of people wanted to do hydrogen generation, carbon hydrogen that can power your cars. The hydrogen generation can be done with greener technologies, with glucose, sucrose, or bio-based material. Efficiency are getting improved currently. Those type of things are happening. We are also now becoming better and better to convert solar energy to electricity. So solar panels are becoming more efficient, somewhat greener than what they used to be. We are having somewhat good approaches to recycle some of the solar cell, utilizing the same silicon for the next generation of solar cell. So those are the technologies. Technologies like this, you take, for example, carbonaceous material. If you do not take this plastic waste to make the carbon, currently we are taking gasoline that can do something better, and then converting that into the carbonaceous material. The carbon has so many applications in the world, correct? You have carbon in your tire industry, your filtration industry, your printer and toner ink that you are using today, 15, 20 micrometer diameter particle, those are all carbons. So instead of using hydrocarbon to generate that carbon in the company, you can take those trash-based material, get rid of them, and at the same time you make value-added material for our society, and that can be useful for various applications. So those are the new technologies coming up with their pros and cons, but we have to see how we can make them effective in order to utilize.
Thank you for sharing those breakthroughs. It was truly inspiring to learn about the future of sustainable energy. My next question is, your research has explored innovative approaches such as the converting waste materials into advanced carbon materials for energy storage. How promising is the concept of energy waste to energy materials in addressing both environmental and energy challenges?
So if you really carefully think how we start and how we are ending up. So for example, I gave briefly some information that we are taking small amount of, let's say, plastic or waste, putting inside the reactor. We do not allow anything to release to the atmosphere, no carbon dioxide, no carbon monoxide, no carbonaceous material, although we want to make the carbon. You cannot release to the atmosphere, otherwise there will be inhalation problem. So while developing the technology, we make sure that it is greener, or whatever we have it, better than that, without releasing to the atmosphere anything substantial. At the same time, it is economical. More than that, we also look at that whether it is scalable. So I showed some of the concepts that are scalable. The second system I showed where we have these carbonaceous material spherical shape made, that is a high temperature, high pressure reactor that has a issue to scale it up. The first approach I showed where we took the packing peanut and scale it up to kilogram quantities, actually that can really do well in a way that you can make kilograms and eventually tons of the material, use it for different applications that includes batteries, solar cell, water purification, tire industry, and so forth and so on. So there are better ways to do that without taking any hydrocarbons that we are doing that today. We are also doing it at lower temperature. We don't want to go to 1000, 2000 degrees Celsius temperature. The carbon I showed you on of the slide, the best carbon we buy for the battery industry, that is very expensive because it is treated at very high temperature. We want to keep the energy requirement low. So there are some issues to scale up some of the technologies, but there are technologies that can be scalable without hurting the environment and also economy.
Thank you for shedding light on the potential of waste to energy materials. It was both insightful and inspiring. My next question is, despite rapid advancement in research, many sustainable technologies take time to reach large-scale implementation. What are the major scientific or economic challenges in translating green material research from the laboratory to real-world applications?
Yeah, for example, this plastic recycling problem is there for hundreds of years. Plastic came to us 100 years ago or so. Many people are trying to develop whether I can really take that long chain polymer, eventually make a small chain and convert again into the long chain polymer. For example, polyethylene. All the plastics bags are made from polyethylene. There are two kinds of polyethylene, the high density and low density. The grocery bags, which are non-transparent, that is high density polyethylene, and the transparent bag are low density polyethylenes. For example, it is so simple molecule, it has carbon and hydrogen. We want to recycle that to another carbon and hydrogen. But in polymer science, what happens is you take a long chain molecule, recycle. During the recycling, it becomes small chain and then small chain and small chain. Once it is very small chain polymer, you cannot make a bigger polymer effectively without consuming a lot of energy. So that's why these plastic recycling companies are successful, but very limited. If you Google now, in the whole world, how much plastic is getting recycled, maybe 10, 15% or so remaining still goes to the landfill because it is not economical, it is not sustainable. Corporations are not making any money recycling your plastics. More than that, the plastic is also not clean. We mix it up. For example, polystyrene, polyethylene, polyethylene terephthalate, we mix it up and then throw it away. Now, there is no foolproof technology in the world. There is IR technology. We can detect the polymers when they are separated. But if we have a polyethylene and polyethylene terephthalate on the top and then polystyrene, and then the IR is trying to detect the plastic hide underneath, and you can detect and separate or sort out. So there should be some technology that pre-sort the plastic before it goes to the recycling facility. So such things should happen in industrial scale. For example, all the polystyrene should go in one side. Polyethylene terephthalate, all your Coke bottle, water bottle, they should go separated from all other polymers. Then it is somewhat feasible, easier to recycle. Otherwise, plastic recycling itself is complex, and we are making it more complex, just putting them together and making our life much difficult. And then eventually, even very sophisticated places you go, for example, airports, they have 2, 3, 4, 5 bins that, okay, put the bottles here, put the food trash here, coffee cups there, this and that. But eventually you see that they ask us to separate. Sometimes we have some leftover coffee, we dump it and we are done. But who can recycle something like that? More than that, if you see what happens at the end of the day, the person who cleans the airport or the trash, he take all your plastic and put it together. So whole day you separate out and somebody put it together and put it in one truck. And I don't know where it goes. But this is what we do. We do a lot of hide and seek in our day-to-day life. One should not do that. And that's why the success rate is still low, because we try not to effectively sort it out. And once it is sorted, not to mix it again. So to answer your question briefly, to make anything sustainably recyclable, economical, we have to pre-sort the plastic. So, for example, you have a vending machine and you go to the vending machine and buy Coca-Cola or let's say Pepsi, whatever drinks, water you have. Now, what you do, you put the money in and you selectively put the button and say that do this one or give me this one. Likewise, we have to have a machine. When you are done with the plastic, you bring it back and then push the button and ask that machine to take your plastic back, and then it start recycling there in the airport itself, for example. If we have that pre-sorting machine, then you have the polyethylene terephthalate, all the bottle-derived plastic. Then it is already sorted out. Then that directly goes to company and they make another bottle out of it. Otherwise, when you mix it up, it becomes too complicated.
Thank you, sir, for sharing your insights. My next question is for students interested in pursuing careers in sustainable energy, material science, or green technologies. What key skills or interdisciplinary knowledge area should they focus on during their academic journey?
So this sustainability topic is there. It was before me, it was there. And still we have hassle. And we have something today that was not there. For example, you are all machine learning people, AI, artificial intelligence learning people. Actually, this can do wonderful things to this sustainability today. For example, we are talking about the materials generation, materials are in this country, that country. If we don't have, we cannot do well. But now we have that data set, who has the material, how much material they have, what we can do with that. Now, all these machine learning technologies can be implemented to sustainability, and where you guys can play a significant role. For example, whatever data we are generating, just giving you an example of batteries, correct? Battery has lots of material, let's say 20 elements inside the battery. It has hydrogen, it has carbon, it has fluorine, it has electrolyte material, it has cobalt, it has nickel, many materials from the periodic table. Now, we know how many batteries are there in the world. Let's say 20 billion batteries are available to recycle. Now, if you really come up with the idea that I will have a recycling company in India, for example, where we will make material required for the new batteries out of the waste batteries. So AI, you can take the help, who are generating the batteries, where they are trashed, how can we get together? All that data can be together, learn from that, have a facility where all it is kind of central place, and then start recycling. And once you start recycling, it will become profitable in a larger scale with some innovative technology, without creating too much acid or bases. So we have to have all this data coming together, actually developing new ideas, innovative ideas. You don't have to go anywhere today. You don't have to even go to the library. You just sit in front of your computer. All these new tools, correct? Perplexity, Google Gemini, you might know much more than me. All those tools are doing a wonderful job. They have access to all the publication. Whatever I publish today, that is already there online, and all the website knows that. So if you ask any genuine question, it has answer for you. For example, you are asking Google Gemini, where is the largest amount of plastic produced today? It will give you the answer. So you know your recycling facility has to be next to it and not somewhere else. So any question answer you can ask to these all new technologies using AI for good purpose. This is where new generation should be focusing and actually accelerating the way we are working today, correct? We are still very slow on recycling and sustainability. This AI can help you accelerate the pace, the discoveries. And I think that is what one should be focusing.
This gives a strong understanding of what students should focus on during their academic journey. Thank you. My last question is, looking ahead to next 10 to 20 years, how do you envision the role of green materials in shaping global energy systems and addressing climate change?
Yeah, so everything works with the material. So if it is greener, that is the wonderful. Not only 10 to 20 years, it is going to change us. It is going to change forever, correct? Once you develop the technology, such as cell phone we developed, we understood how the materials are working. Now that cell phone changed another hundreds of generations that will come on our earth. Material science will continue to develop, continue to bring new technologies to us. So if you are using the material that is sustainable and greener, that is going to be in that technology. So not only 10 to 20 years, but I think for all future perspective, if you extrapolate to hundreds of years, greener the better, less CO2, good for us, many good things could happen. Today, we are only taking care of carbon dioxide by nature. If you look at it, outside we have trees. Those are the trees only doing greener things, taking your carbon dioxide expelled through your body or coming out of your car or the truck. Only it has the ability to take it and give back to you oxygen. We are thinking about too much on the material side, developing new technologies. Actually, technologies, whenever you develop, it always makes something worse to the environment as well. On the contrary, we also have to think that how can we continuously go on planting those trees? If we ask a simple question to ourselves, we are on this earth for whatever years, 20 years, 30 years, 50 years. We took so much oxygen from the nature. How much oxygen you produce or help nature to produce? How many trees we planted? Actually, if we really think carefully and write down on the paper, we did not produce enough trees ourselves to give back to the nature. We use much more oxygen than nature gave us. Nature gave us a lot of oxygen. We did not produce enough oxygen, and we can help nature to do that just by planting more trees. But we forgot that. We go to more sophisticated thing and simple thing we forget. Again, coming back to your question, materials will help. If it is sustainable material coming from the nature, going back to the nature, it would help us to keep us greener and sustainable.
It's fascinating to see how green materials could transform energy systems in upcoming decades. Hello participants, do you have any questions? If yes, please unmute yourself and ask questions.
Yeah, can I ask one question? Yeah, Professor Paul, I enjoyed your talk. Thank you very much for enlightening us about green materials and technologies for tomorrow. So my question is, because in different parts of the world, lots of conflicts are happening, and during that process, lots of carbon dioxide, carbon monoxide, nitrites, when bombing is done in the dark clouds of the smoke, there are lots of hazardous gases and chemicals, and including this carbon dioxide and carbon monoxide. So from environmental health perspective, how you think all these how we can take care of all these things, because environmental health is very important for us to stay healthy. Without healthy environment, we cannot be healthy, right? From one health perspective. So any thoughts on this one?
This is a question that really everybody should think. All the technologies we are developing, sometimes it is good for us, sometimes we are trying to destroy each other. But at the same time, people are not thinking that while hurting others, we are also getting hurt, correct? Once you release the carbon dioxide to the atmosphere, it doesn't matter what part of the world you released it, correct? For example, if we say that Asia is very good in making the batteries, correct? China, Korea, Japan, they are making good batteries, and that's why India, US, and all other people are enjoying it. All our cell phone batteries, if you open up, they are made in Asia. Now, they release already a lot of CO2 while making them. Now, when you land there on their airport and say that it is all dirty here and dusty, actually you contributed to that, correct? We are not thinking about that. There is industrialization. The industrialization is going to produce carbon dioxide, and they already produced it, and we contributed to that. And that's why I mentioned at some point that we have to be really thinking whole spectrum life cycle analysis of any system that we develop. And I think we are all half literate people, including us, where we have very limited knowledge on any technology. So we believe it is okay to do whatever we are doing. But when we completely do the life cycle analysis of materials, starting from the scratch all the way to technology and going back to the nature, how green it is. Most of the materials, 90+% materials, are not really green. Now, coming to this fog, carbon dioxide happening with the war and things like that, that is also really devastating and very bad for the environment. It is going to hurt now, or it is hurting already, or it is going to hurt for future generations. As you mentioned, that environment is a key thing. In Pune, Mumbai area, there is so much population, so many cars for unnecessary reason. We brought it to the road. We think that we have some better standard of living, but we actually brought our standard of living down, because the same year, as soon as you step out of the car, you are inhaling the bad air that goes to your lungs, and how long you can take it. So it is all interconnected problems. Therefore, all the technologies, all the materials discovery, whatever we are developing, including any sophisticated, correct, our laptops, for example, we have very nice sophisticated technology. It has so many other elements inside, and those are not green. When they are done, the end of the life of the laptop, we are going to trash it or do something with that. We have to be very thoughtful where we are going to trash that. So without going to very complex problems, your question is really valid. Everybody should think carefully while they are utilizing, using anything. For example, your water bottle, correct, a half-liter water bottle, plastic bottle. It is very easy to drink that water in 30 minutes. In summer in India, you might drink it in 3 minutes. And as soon as you generate that bottle has 300, 400 years of life. Your life is limited here, 70, 80 years. We are going to disappear. But we are creating problem for next 3-4 generations continuously. In America, a developing country like us, where we are generating minimum 200 kilograms of plastic every year, minimum. Our weight is less than that. In India, might be the same story. Now, we do not know how to really get rid of the plastic, how to recycle. Then can we reduce utilization of that? If we can do that, that is the best way to do it. So if we can reduce utilization of all that dangerous things, that can also help us to survive. Population growth is happening, although it is slow now, but it is still happening. There is a population. So for all this population, we have the same resources. Same land is available. Only 30% land in the world, 70% covered by water. Then with that 30%, do we have enough things that can be produced? You use a lot of fertilizer. Some of the land is becoming barren, not going to produce any more farm fruits that it used to. So we have to be really thinking that what we are trying to do, what we are accelerating, and really are we accelerating it or going in the negative direction? So there are many pros and cons with every system that you have in hand generating CO2. People are talking about this negative carbon dioxide sequestration. Without thinking, we are doing it. For example, all these cold drinks, carbonated drinks, they are carbonated. There is carbon dioxide, literally carbon dioxide inside, pressurized and put it inside. Who asked us to drink that? How bad we are, correct? Nature tells us that take oxygen inside. When we breathe the air, we take oxygen and release the carbon dioxide. Our body does not like the carbon dioxide. But we are all fancy people. We drink carbon dioxide ourselves and then release to the atmosphere. So we are actually contributing to release the carbon dioxide. You don't have to go to the car exhaust. You drink the Coca-Cola and you are releasing CO2 because it is pressurized and put it there and you are bringing to the nature. So those type of things we need to really think carefully. There is carbon everywhere. How we can sequester that, starting with our own examples.
Yeah, thank you very much. Rishita, go ahead.
All right, fellow students and esteemed participants, that concludes with a truly enriching discussion. Thank you very much, Professor Paul, for sharing your such invaluable insights and thoughtful responses. Your perspective has certainly inspired our students and participants to think more deeply about the role of science and innovation in building a sustainable future. To all our participants, thank you for your active engagement. With that, I now hand the session back to our MC. Thank you, Ms. Pratiksha, over to you.
Thank you, Rishita, for skillfully moderating the session. To formally conclude today's program, I now invite Ms. Samriddhi to deliver the vote of thanks on behalf of the entire organizing committee. Ms. Samriddhi, over to you.
Thank you, Ms. Pratiksha. Hello, everyone. Respected dignitaries, faculty members, and dear fellow students. I am Samriddhi Srivastav, a proud BSc Biotechnology student at the Department of Biotechnology and Microbiology, Center for Scientific Research and Development, People's University, Bhopal. It is indeed both an honor and privilege to propose the vote of thanks on the behalf of organizing team and the Center for Scientific Research and Development, People's University. As we draw the curtains on today's enriching session of the BioConnect webinar series, first and foremost, we extend a heartfelt gratitude to our distinguished guest speaker, Professor Dr. Vilas Pool, for graciously taking time out of his busy schedule to be with us today. His insightful presentation on green materials and energy technology for tomorrow has been truly enlightening. We are sincerely grateful for the knowledge and wisdom you have shared with us. We also extend our sincere thanks to the Honorable Vice Chancellor of People's University, Professor Dr. Harish Rao, for his presence and encouraging opening remarks. Sir, your continued support is highly appreciated. A heartfelt appreciation goes out to all the respected dignitaries who joined us today. Your presence has added immense value to this event. We extend a heartfelt gratitude to our mentor and guide, Professor Dr. Subhash Bhore, sir. Your vision, guidance, and constant support have been driving force behind this webinar series. Your mentorship continues to inspire, empower, and motivate us. We thank our moderator, Ms. Rishita Maurya, for skillfully moderating the session. I would like to take a moment to highlight the essence of BioConnect for the student by the student initiative. It stands as a testament to the remarkable heights passionate learners can reach when given a platform to explore, question, and grow. Through this series, we not only gain insight from global experts, but also nurtures a vibrant academic community driven by collaborations and curiosity. To our ever-enthusiastic audience, thank you. Your participation, engagement, and thoughtful questions brought energy and substances to today's session. Your presence truly makes all the difference. And finally, we express our most profound appreciation to the management of People's University for their unwavering support and encouragement. Your belief in student-led activities such as the BioConnect webinar series enable us to dream big and achieve more. With that, I now hand it over to our MC to continue with the proceedings. Again, thank you. Ms. Pratiksha, over to you. Thank you.
Thank you, Samriddhi, for expressing our sincere gratitude to our respected guest, our speaker, and all the participants who joined us today. Dear participants, your feedback is extremely important to us. We kindly request everyone to take a moment to fill out the feedback form, the link to which has been shared in the chat box. Your valuable suggestions will help us improve the quality and relevance of our future webinars. Now, we will wait for 2 to 3 minutes while participants submit their feedback. We hope you have had a moment to share your feedback. Please note that your e-certificates will be sent to you on your registered email addresses shortly. With that, we come to close of this insightful session of the BioConnect webinar series. We look forward to bringing you many more engaging sessions that connect science, society, and students. I'm Pratiksha, signing off on behalf of the CSRD students team, People's University Bhopal. Thank you all for joining us today. Wishing you a pleasant and inspiring evening.
Thank you. Good luck.